Okay, welcome back. And now we're going to move on to the next section in the Gordon-West manual, which is called weak signal propagation. And actually, even though it's called weak signal propagation, really this section is just sort of on propagation in general. So we're just going to be looking generally at propagation. Okay, what exactly is propagation? Because that might be a word that's a little unfamiliar to you. So to find out what propagation is, let's go to our good friend and the best source of information ever, Google.com. And according to Google, propagation is, it says, quote, radio propagation is the behavior of radio waves as they travel or are propagated from one point to another or into various parts of the atmosphere, end quote. So basically what this means is propagation is just the travel of radio waves as they go from point A to point B, one point to another. So the first term that you need to know for radio propagation is the radio horizon. Radio horizon. I also wrote propagation on the board here. You can write that down. But we're going to look now at radio horizon. So when we say radio horizon in ham radio, radio horizon means the distance over which two stations can communicate by a direct path. That is from the signal just going from one person straight to the next person. So radio waves, they often go in a straight path from point A to point B. For example, if you look at this diagram of the Earth here and pretend these are two hams, the radio signal might just go from this person all the way in a straight line to this person. That's pretty simple. Point A to point B, a straight path. And this is also called line of sight because obviously this figure is sort of exaggerated, but pretend these people are standing close enough together so that they can actually see each other, even though they're far away, but they can see each other. So if you can see the other person that you're talking to, then obviously you can hit him with ham radio because the radio wave will just be able to go straight there. There's nothing blocking your view. And on the other hand, if you for some reason can't see this person, maybe there's a big mountain in the way, if you can't see the person, then you might not be able to hit him on ham radio either, because if you can't see him, that means something's blocking your view and something may block the radio wave as it tries to travel as well. So that's called line of sight. The radio wave often goes by line of sight, meaning the path the light wave takes from this person to your eye, say, that's the same sort of path the radio wave will take, line of sight. So you see, if the Earth were very flat, then we'd be able to communicate very long distances because of this line of sight principle. As long as you can see it, you can hit it. If the Earth was just flat, well, we'd be able to see anyone no matter how far away they were. The radio wave could just zip all the way in a straight line, all the way down that way. But the problem is the Earth is not flat, the Earth is curved. And because the Earth is curved, the path gets blocked, as you can see in this diagram over here. Pretend this guy wants to contact this guy over here. We have a slight problem. The radio wave likes to travel in a straight line. If the radio wave travels in a straight line, it will have to go through the center of the Earth. Radio waves cannot go through the center of the Earth. That's impossible. The Earth blocks the radio wave. The radio wave just can't go through that. Radio waves travel through space. They don't travel through solid objects like the Earth. So then the radio wave never gets to this other person. And we could aim the radio wave up this way so it doesn't go in the center of the Earth, but then it just sort of goes up here into space and it never gets to this guy either. So we have sort of a problem. But this is what we call the radio horizon. It's the distance over which people can communicate over a direct path. So here these people can communicate straight line of sight. Here these people cannot, and that's radio horizon. Radio horizon is limited, as you can see, by the curve of the Earth. And again, these drawings are sort of exaggerated, by the way. Normally, you would actually lose sight of the person due to the curve of the Earth after about 5 miles, not necessarily the amount of distance that you see here. But here's where things get really interesting. It turns out that just because you can't see the other station due to curves in the Earth, it doesn't necessarily mean that you can't talk to them just because you can't see them. Because Earth, it's strange. Radio waves act similarly to light, but they don't act exactly the same. And it turns out Earth actually seems less curved to radio waves than they seem to light. So in other words, radio waves, they sort of bend a little bit, so they can sort of get around this curve a little bit. They're not totally in a straight line. The Earth seems less curved to them, so they can get over the sort of hump. But they can't get over it that much. Radio waves, for the most part, travel in a straight line. But this is really good news because that means our range isn't limited to just 5 miles. We can get a little more than that with this line of sight principle where it's like the radio wave travels the same way light wave travels to and from our eyes. So wait a minute then, something might be confusing here. If that's true and radio waves are limited by the curve of the Earth so they can't get very far around the Earth, if that's true, then how can we talk to people in other countries with ham radio like I told you about? Did I lie to you? Well, no, not all radio signals actually travel by line of sight in a straight direction this way. So some radio waves reflect off the ionosphere, which is a layer in the sky, and we talked about that briefly. We're going to touch on that more tomorrow. But not all radio waves actually reflect this way off the ionosphere, as you probably have noticed based on these diagrams. A lot of radio waves just go by line of sight or in a straight line. So for example, UHF signals, ultra high frequencies, they don't reflect off the ionosphere at all. It's all straight line of sight. So they can't travel long distances because of this curve in the Earth. And that's very important. But HF waves, which is just the high frequency waves, they usually do reflect off the ionosphere. In fact, they reflect a lot. And we're going to look more at that and what the ionosphere is. We're going to explore that more in tomorrow's video lecture. But for now, we're going to look at other things you can bounce radio waves off of first, such as auroras. You can actually bounce radio waves off of auroras. So you've probably heard of the aurora borealis. It's a big show of auroras in the North Pole. And if you go to the North Pole or even Alaska at night, you can often see the aurora borealis. And this aurora borealis and auroras like that, it turns out you can actually bounce ham radio waves off of auroras even if you don't live in Alaska. Isn't that cool? So during these aurora contacts, the signals, so pretend this is the aurora, the signals sort of bounce off the aurora in the sky, and they bounce off, and then you might be able to actually hit this guy over here. Well, actually, you can't get quite that far. But the thing about aurora contacts is the test will expect you to know that during aurora contacts, the signal that you're transmitting, it exhibits rapid fluctuations in strength, and it sounds sort of distorted. So for example, I'm in New York, and I've actually made aurora contacts with people all the way up in New Hampshire on the 6-meter band. And if that sounds far away to you right now, just wait until we start talking to other countries. So the thing is, though, I noticed in this aurora contacts, everybody sounded terrible. It almost sounded like everyone was using a broken microphone. And this is because aurora contacts, they have these rapid fluctuations in strength and they sound distorted. And this is actually an important fact you'll need to know for the exam. Now, if you pass your technician exam and get your license, you can actually operate with your privileges on 6-meter aurora, and you can hear this phenomenon for yourself. Okay, so we know we can bounce signals off auroras. That's one way we can talk to sort of long distances, at least in between states. There's other things you can bounce waves off too. How about meteors? Yes, that's right. You can bounce ham radio waves off of meteors as they're traveling through the sky or in space. So actually, oftentimes you don't actually bounce it off the meteor itself, but meteors, as they're going through the sky, they sort of leave a trail behind them. As you can see here, they leave a trail of basically meteor stuff, meteor dust or something, and that meteor stuff will actually stay suspended in the sky for a few seconds after the meteor keeps going. It'll just sort of suspend there before sort of dissolving into the air and going away. So meteor contacts, usually you bounce your signals off of these trails that the meteors leave behind. And these meteor contacts are really fun because you have to make the contacts really fast. Because, as I said, the trail that is left behind meteors, it does reflect radio waves, but the problem is the trail disappears in a few seconds. So meteor contacts can only last for a few seconds before the trail disappears, and then you can't hear the other person anymore because the radio waves aren't bouncing off the trail anymore because the trail's gone. So meteor contacts can actually be a lot of fun. And actually, the Gordon West manual you have, it came with a CD you may have noticed in the front cover. And this CD actually has an audio recording of a meteor contact if you'd like to listen and know what that sounds like. And actually the CD on your Gordon West manual has a lot of cool and interesting things. And if you haven't already, you can take that out, put it in your CD player, and go ahead and take a listen. Now we're going to look at something else, which is called tropospheric ducting or tropospheric scatter. What in the world is that? Okay, so VHF signals, we talked about how UHF signals can't use the ionosphere, they can't travel long distances. VHF signals, even though VHF signals can sort of travel long distances sometimes, and they do this through something called tropospheric ducting or tropospheric scatter. Now, the theory behind tropospheric ducting and how it all works, it's a little complicated, and it has something to do with the troposphere, as you may have guessed from the name. But it's sort of beyond the scope of this course. So all I'm going to tell you, and all that you need to know for the exam, is that tropospheric ducting and tropospheric scatter, it sometimes allows VHF and maybe even UHF signals sometimes, it sometimes allows them to span 300 miles. Wow, that's amazing. It doesn't happen a lot, but when this does happen, it's pretty cool. So tropospheric ducting, you do need to know what causes it. And tropospheric ducting is caused by temperature inversions in the atmosphere. Okay, so what does that mean? Well, think about it this way. You know, maybe you've noticed when you're driving around on a hot summer day on a highway, or maybe your parents are driving around on a hot summer day, and you're driving along a highway pretty fast, and you feel like you look ahead and you think you see some water on the roads, like some water on the highway, as if there's a flood or something. But then you get nearer to it and the water sort of disappears, and you realize it's just there's a lot of heat and it's creating some sort of illusion, almost like a mirage or something. And this is actually a temperature inversion. What you're seeing is temperature inversion. And the same sort of temperature inversion also causes what we call tropospheric ducting. And again, the details are beyond the scope of this course. But all you need to know for the test, it's very simple, and you can write this down if you need to. Temperature inversions cause tropospheric ducting, which cause VHF and UHF waves to travel 300 miles when that happens. So that's all you need to know for the exam. So we're almost done, and there's just one more thing really you need to know, and that's called knife edge diffraction, what we call knife edge diffraction. So what's that? So knife edge diffraction is when radio waves, they sort of bend over a mountain or another sharp obstruction. And when this happens, a signal that would otherwise be blocked by the obstruction, it can sort of go around it and reach the other side. And this way, you might think that if you live over here and your buddy lives over here and there's a mountain in between you guys, you might think you might not be able to talk to the person because of the mountains in the way of the radio signal. But because of this knife edge diffraction, sometimes the radio wave can actually go up and around the mountain. So let's look at actually what happens here. So what happens is a radio wave, it might go up a mountain. See, the radio wave starts to go up a mountain, but when it hits the sharp edge of the mountain, what happens is it actually sort of bends around a little, actually. And your Gordon West manual explains this a little more. But the radio wave sort of, when it hits something sharp, it sort of bends. And so what happens is, if you're over here and you're trying to transmit over here, the radio wave can actually bend over the sharp tip of the mountain and go back down the mountain and get to your buddy who's maybe over here. So it's almost as if the radio wave is climbing up the mountain and traveling back down, as if it's a person who's actually climbing the mountain. And this description, it might not be 100% accurate, but it's close enough for the test, and it's the easiest way to understand knife edge diffraction. So that's pretty cool. Now you might be wondering why knife edge diffraction is called knife edge diffraction. And this is because the mountain is sort of like a knife edge. The sharp tip of the mountain, the sharpness of the mountain, it's sort of like it reminds us of a knife edge. And the knife edge diffracts the radio wave signal so that it goes sort of around that tip or around the sharp edge. And it doesn't have to be a mountain. It can be a building or some other large obstruction as well.